This higher chemistry video on intermolecular forces is going to focus on a particular type of intermolecular force called hydrogen bonding. And in this video, we're going to look at how those hydrogen bonds arise and their relative strength compared to other intermolecular forces. These are the outcomes we're going to look at today. So I'm not going to read them out to you, but basically today we're going to look at some boiling point data. We're going to look at the definition of a hydrogen bond and also the relative strength compared to other types of bonds. So the first thing we're going to look at are the boiling points of hydrides of group 4. So these are the elements present in group 4. We've got carbon, silicon, germanium and tin. When they join with hydrogen to form a compound, we call them hydrides. So we've got carbon hydride, silicon hydride, germanium hydride and tin hydride. The first thing I want you to consider is, as we go down the group, what will happen to the boiling points of the hydrides as you go down a group? Will they increase or decrease? And also, what would be the reason why? So try to give as much detail as possible. So pause it, write down or think of the answer in your head, and then we'll go through what the answer is. As we go down from carbon down to tin, you'll see that the number of electrons in the molecule increases. This means the strength of the London dispersion forces between the molecules also increases. Therefore, the boiling point will increase for each element joined to hydrogen as you go down a group. So carbon hydride will have the lowest boiling point, tin hydride will have the highest boiling point. And you can see from the data here, carbon hydride has got the lowest boiling point, and there's an increase in boiling point as the hydride has more electrons. So this is what you'd expect if you're relating the number of electrons to London dispersion forces, is these need to be overcome when you melt or boil these hydrides. Remember, we're not breaking the strong covalent bonds within the molecule, we're breaking the intermolecular forces between the molecules. We're now going to look at the boiling points of hydrides of group 5. Group 5 contains the elements from top to bottom: nitrogen, phosphorus, arsenic, and antimony. And when they form hydrides, they join to 3 hydrogen atoms. Notice that as we go down the group, the number of electrons in each molecule increases. So we would expect the London dispersion forces to increase between the molecules too, and therefore the boiling points to increase, like with the group 4 hydrides. However, when we look at the trend in boiling points, we can see that ammonia, NH3, has a higher boiling point than you would expect. You'd expect, going by this trend, it would be down here about minus 130 degrees Celsius, but it's a lot higher than that, despite having the fewest electrons. We're now going to look at the boiling points of the hydrides of group 6. Group 6 contains the elements oxygen, sulfur, selenium, and tellurium. When they form a hydride, each of these elements joins to 2 hydrogen atoms. And you'll notice again that as we go down the group, the number of electrons in the molecule increases. So we'd expect the boiling points to increase as the strength of the London dispersion forces increase. However, you can see there's one data point that's a bit out of sync with the rest. In this case, it's hydrogen oxide or water. We would expect from this graph that hydrogen oxide, having the fewest electrons, would have the lowest boiling point. It would be around about here, about minus 80 or so. But as we know, water has a boiling point of 100 degrees Celsius. So water also has an unusually high boiling point compared to other hydrides in its group. Finally, we're going to look at the boiling points of the hydrides of group 7. So group 7 contains the halogens, fluorine, chlorine, bromine, and iodine, and they each join to 1 hydrogen atom when they form a compound. And you can also see the electrons increase as you go down the group. Like the previous 2 graphs that we looked at, we get one point that's slightly higher than the rest. In this case, when you have hydrogen joined to fluorine, you have a higher than expected boiling point than what you'd expect going by the trend of the other hydrides in group 7. So we can say that hydrogen fluoride has a higher than expected boiling point, just like water and ammonia in the previous graphs. So to summarize, for the boiling points of hydrides of groups 5, 6 and 7 is that when you have a molecule that contains hydrogen joined to oxygen, or hydrogen joined to fluorine, or hydrogen joined to nitrogen, the molecule will have a considerably higher boiling point than other hydrides in its group, despite having the fewer electrons than the other elements present in that group that are joined to hydrogen. So the boiling point of data we've just seen suggests that there are stronger attractions between hydrogen fluoride molecules, water molecules, and ammonia molecules than what you would expect to get, just taking into account London dispersion forces and simple permanent dipole interactions. So to give us a clue as to why intermolecular forces are strong when you have oxygen-hydrogen, nitrogen-hydrogen, and fluorine-hydrogen bonds within the molecule, the key is to look at the electronegativity differences. So I'm just going to have the electronegativity differences of the nitrogen-hydrogen, oxygen-hydrogen, and fluorine-hydrogen bonds. And you can see compared to others in their group, and indeed other groups, they have big electronegativity differences between the hydrogen and these very strong electronegative elements such as nitrogen, oxygen, and fluorine. So we say that these bonds are very polar, i.e. there's a very strong negative charge at one end of that bond and there's a very strong positive charge where the hydrogen is. So let's look at fluorine-hydrogen bond. Fluorine has a high electronegativity, the highest in the periodic table with a value of 4.0. So the electrons are going to be strongly drawn towards the fluorine in that covalent bond, forming a polar covalent bond. So we have a highly negative charge at the fluorine end and a high partial positive charge at the hydrogen end. Nitrogen has an electronegativity value 3, it's got a fairly high value, so it's going to contain quite a polar bond as well. And the same goes for oxygen, which has an electronegativity value of 3.5. So it will have a highly polar bond as well. So we can say because fluorine, nitrogen and oxygen have particularly high electronegativity values, they will form highly polar covalent bonds compared to other bonds that we will come across. So if we have molecules containing highly polar covalent bonds such as hydrogen joined to fluorine, or oxygen joined to hydrogen, or nitrogen joined to hydrogen, we have particularly strong permanent dipole interactions between the molecules. And these particular type of stronger permanent dipole interactions we call hydrogen bonds. So here's an example of a hydrogen bond between two hydrogen fluoride molecules. And here are examples of hydrogen bonds formed between water molecules and ammonia molecules. Note that these are intermolecular forces. They're not actual bonds like covalent bonds or ionic bonds. The word bond is a little bit misleading. This is actually an intermolecular force or a type of van der Waals force. So you can summarize the electrostatic forces of attraction between molecules containing these highly polar bonds containing hydrogen fluorine, oxygen nitrogen, or nitrogen hydrogen are called hydrogen bonds. Note that it's the intermolecular forces between the molecules that are called hydrogen bonds. This bond here, the covalent bond, isn't the hydrogen bond. It's the forces between the molecules containing these bonds that are hydrogen bonds. One of the skills you will need to acquire during the course is to look at the structural formula of a molecule, look at the functional groups, and determine whether hydrogen bonding can occur between the molecules. So for hydrogen bonding to occur between the molecule needs to have covalent bonds containing hydrogen joined to fluorine, oxygen joined to hydrogen, or nitrogen joined to hydrogen. So here are a selection of molecules that can hydrogen bond to each other. So we've got hydrogen fluoride. That's one example we've looked at already. The one I've circled here is adenine, which is a base which is present in DNA. So it can form hydrogen bonds with other bases, and this hydrogen bond interaction within DNA allows it to unzip when the hydrogen bond breaks. So it's an important bond in nature. We've got ethanol here, which has got an OH group, and below ethanol we've got glycerol, which has got 3 OH groups, so which can form 3 hydrogen bonds. We've got an amine here with an NH group, and at the bottom right we've got an amino acid, which has got an amine group at one side and a carboxylic acid at the other. So I'd like you to have a go at this question. Guess A, B, C or D and see if you are correct. So pause it and have a guess. Okay, so the first thing we're going to look at is which ones would hydrogen bond. What functional group should it contain if it can hydrogen bond? Well, we're looking for HF, NH or OH if it can hydrogen bond. If those are not present, then it won't. Well, this one's got an NH group, this one's got an OH group, this one's got an NH group, but this bottom one contains neither HF, NH or OH groups. This is an ether and therefore it will not be able to hydrogen bond with other molecules. As well as looking at the structural formula of molecules and identifying functional groups that allow the molecules to do hydrogen bonding with each other, you need to know the relative strength of hydrogen bonds compared to other intermolecular forces and other types of bonds. This is a table summarizing bond types and their strength. The top 3 are bonds you would get between atoms and ions. These are strong bonds, such as metallic, ionic, and covalent bonds. These bonds are not broken when covalent molecular substances are melted or boiled, unlike the bottom 3, which are intermolecular forces, collectively known as van der Waals forces. These are forces between molecules of which hydrogen bonding is the strongest, followed by permanent dipole interactions, followed by the weakest intermolecular force, London dispersion forces. So to summarize, the forces we get between molecules, i.e. intermolecular forces, are collectively known as van der Waals forces. The weakest of those forces are London dispersion forces, followed by permanent dipole interactions, of which we have a stronger type of permanent dipole interaction called hydrogen bonding.